Nigel Xiao, the Deputy Director of the Seismology Center of the CWA, Central Weather Administration. Today I am very honored and glad to host this online meeting. I think maybe it's the first time for the Jma and the CWA on the topic of for the earthquake and the tsunami for the discussion. So it's our pleasure, it's our honor for us to have the online meeting. First, I think because just like Japan, Taiwan is also in the seismic active zone, so a lot of earthquake and tsunami here. So I think the communication, even in the future, had the more communication, even the cooperation in the future. I think it's very important for both sides. So today we are glad to hear the possibility, and I would like to say that Jamie to arrange the agenda for us. So maybe we can follow the agendas to have this afternoon's meeting. Okay. Okay. So I think before the meeting, I think maybe we can have introduce ourselves before the meeting. Okay. Okay. So maybe for the JMA, would you please to introduce your participant for you? Thank you.
Okay. At first, I'd like to introduce from JMA side. At first, I'm Yasuhito Sumida. I work in the Office of International Affairs. So today I coordinate collaborate with you. And after that, I'd like to introduce earthquake division person.
So my name is Nariaki Okawara from Science Earthquake and Tsunami Monitoring Division.
Okay, nice to meet you.
My name is Dr. Suzuki. I belong to Administration Division of Department of Disclosure and Technology. It's my pleasure to participate in this meeting. Thank you.
Okay, thank you.
My name is Junichi Okawari. In Earthquake and Volcanic Division. I'm Muraki. Same division.
Okay.
Thank you very much. This is from Jma headquarters. Please transfer to the Meteorological Research Institute.
Okay, so my name is Miki Hoshida. So some of you already know each other, so you have some time to discuss in the international meeting. So thank you very much for having us this important meeting.
Okay, thank you. Okay, thank you very much. Now for our CWA site. So, Dai.
Okay. My name is Dai Chen. I'm in charge of the earthquake early warning system for CWA now. So later I will give a talk. Thank you for arranging the meeting.
My name is Jma Eew. It's my honor to enjoy this meeting. Thank you.
My name is Guan Yisong. I am now developing the earthquake early warning in Taiwan, and also cooperated with Dr. Chen. Yeah, thank you for using it. Yeah. My name is Zhang Yuxuan.
Okay, so I see the schedule we have arranged. So after the introduction, we have the photo section. What is the photo section? Maybe photo.
How about the screenshot from if you mind, I take a screenshot of my PC. So after that, I will share the images. And also, there are some people from the Meteorological Research Institute of Jma. So maybe other two people from Jma side. Sorry. Please go ahead. Kodera-san, and after that, Inamori-san.
Hi, I'm Michi Kodera from MRI. I'm a researcher of earthquake warning, especially on the wave-based method. So thank you.
Thank you. Okay.
I'm Inamori from the Japan Time and Exchange Association. I hope this conference is a success.
Okay, thank you.
Okay, thank you so much.
Sumimasen, I have the question. Can we hear to record the video? The meeting, can we have the recording?
How about Inamori-san? Is this meeting is recorded or not?
Not. Just a minute. I started.
Okay, thank you.
Okay, I can check the recording. Okay. If you mind, please turn on the screen. I'd like to the screenshot.
Okay, どうぞ。Please.
我们还没开吗？
我想要确认一下他们看不看到我们画面，
对，
这个很重要。
Hey, can you see my screen? Can you see the screen of the CWA? Can you see us?
Yep.
Okay.
Maybe how about seismology center? Maybe one person from seismology center who CWA.
Oh,
It's difficult. It's okay.
It's okay. Actually, we only have one connection. I think the later one is the older one, not for currently using.
所以那个可以拿掉。
我不知道他怎么拿掉。
他是因为他是会议主办人，所以他会留在那边。
哦，
对，所以可能上不到。对。
Okay, I understand.
Okay.
So I'm really confusing. Okay, thank you.
Cool. So please take a photos, please.
Okay. Actually, one other people come to the meeting and he is the presenter. So just now I'm finishing introduction time. So please.
Please.
Nice to meet you.
Okay, thank you so much. And next time, try let's get the screenshot of the session. So please enter the screen. もうちょっと前に微妙に後ろに。Okay. I will take a screenshot. Wait one moment.
Okay, thank you.
Okay, 3, 2, 1. Wait 1 minute. Okay. Sorry, one more, please.
Okay.
Okay. 3, 2, 1. Okay.
Okay. So please send a copy of the photo to us. Thank you.
Okay. I will share you after the meeting. So now, I will share the image. I can take a photo like this. So I will share this screen. Thank you very much.
Thank you very much. So, should we start the following schedule?
Yes, please. Thank you.
Okay, thank you very much. And then in the following, I think there are two sections. The first one is for earthquake early warning systems. So according to the schedule, the first one is presented by the CWA people, and the Dr. Chen will have the presentation for the earthquake early warning in Taiwan. So please.
Okay. So I'm trying to share my screen. Can you see my PowerPoint file?
Yes, I can see it.
Okay, thank you.
Okay. So nice to meet you online. And it's my honor to introduce the Central Weather Administration Earthquake Early Warning System. So here is my contents for today's talk. I will review some recent damaged earthquakes in Taiwan and talk about a little bit about the background of the early warning system and some ongoing projects. And finally, I will provide some discussion points, which I already sent by email. There are five topics we are going to discuss about that. And I will focus on give more time for the discussion points. Okay. So first of all, I want to review some damaged earthquake. This one with magnitude 6.6, which occurred in 2016. At the time, one tall building just collapsed and caused a lot of serious damage for the southwestern Taiwan at that time. And another very new earthquake occurred this year, January 21, and with magnitude 6.4. Again, it occurred in the southwestern Taiwan, and at that time, not so large earthquake damage at that time, but we recorded some very high PGA values for this earthquake. And now I just briefly talk about our seismic network. You can see here, we have two seismic network. One is we call this CWASN. The other one is TSMIP. Most of them are online stations transmitting the real-time data to Taiwan, to our center. And here is the pictures of some of our seismic sensors. And the detailed information is about this. Right now we have a FBA force balance accelerometer instruments, about 275. We also have broadband instruments, and some of them deployed on the surface, some of them in the borehole. And we also have some short period instrument, which is the S13 sensors from the Geotech. We have about 72 sensors, and we also have some ocean bottom seismometer. Totally is 9 stations around the eastern offshore area and the south offshore area, and it's a cable-based system, just similar to the SNET system. And totally we have 611 strong motion sensors on the surface. Okay, so here you can see we have the ocean bottom seismometer, which is a cable-based system deployed around the offshore area, and we also use the data from the seismometer for earthquake locating, using in the earthquake early warning system. But currently, we only take the P wave arrival time for location. We don't use the amplitude from the ocean bottom seismometers for magnitude estimations. Okay, here is our methodology for earthquake locating and the magnitude estimation, and also for the intensity prediction. These are all the formulas we used for our early warning system. And here is some more detailed architecture of our system. We construct the system by using the Earthworm software. Earthworm is a software developed by the USGS and since 1995, and we use this platform to develop our own earthquake early warning modules, and we currently running this kind of system about 10 years for our early warning system. And if you are interested in this system, you can just download by the Docker Hub. We already put the source code, the testing data, and the testing environment. So you just download. It's free, and you can run by yourself. Okay. Here is some specific parameters for our P-wave picker. For fast picking, we need to adjust many parameters for every single individual channels. Usually, we only take the vertical component for earthquake early warning system. So for every station, we need to adjust these parameters. And here is we use two kinds of method for locating earthquake. One is Geiger's method, which is a traditional inversion method for locating earthquake. The other one we call the effective epicenter method. This method is simply by taking the average position, or we can say the centroid position of all trigger stations as the epicenter, and we fix the depth about 10 kilometers. This method is pretty fast, especially for the inland earthquakes. And the epicenter error is not so big because we have very dense seismic stations. So we use this kind of method for, especially for the shallow and the inland earthquake. We can very quickly issue the warning to people. And here is some detailed information about how we measure the earthquake magnitude. Now, one thing I want to mention is we updated the P-wave information from 2 seconds to 9 seconds time window after the P-wave arrival. We're using the maximum displacement values from the P-wave from the vertical component, and use the PD, peak displacement, put into this formula. Then we can obtain each individual magnitude for every station, and after that we take an average, and we remove the outliers, take average, and got the final magnitude for the earthquake early warning system. And once we have a magnitude, we have a hypocentral distance from the target to this focal, the source location. Then we can calculate the predicted PGA, and we convert to intensity. And right now we use two formulas for estimating the PGA, predicted PGA. The cut point is the magnitude 6.5. Larger than 6.5, we use this formula. Small earthquakes, we use this one. And right now we issue early warning system, early warning messages for people through 3 channels. The one is for government agency, for schools, for some users from the app. And the other channel is for television. The other channel is for the cell broadcasting system by the text message from the cell phone. And here is a threshold for the warning for issue, and especially for this one, the public warning system. This one we added one more conditions for this. Originally, magnitude reached to 5, and the PGA reached to 25. We issue, but recently we found some predicted intensity maybe not so large as 25. Still, people can still feel very shaking a lot seriously, especially for people in a high building. And so we decided to add this one more conditions. Once the magnitude can reach 6.5, the intensity, the PGA predicted only intensity 3, then we issue the warning for the public. Okay, here is our development from 2010 to 2025. You can see the blind zone area radius is become smaller and smaller. The main reason is we have more dense seismic station from 2010 until now. And you can see these figures. 2010 station distribution is in the middle, and 2016 is like this, and currently is very dense than before. So we can easily to improve our response time, to reduce the response time. And here is an example for you to show you our early warning performance for the earthquake occurred this year. And we issued a warning to people about 7.9 seconds after the origin time. This is the first alarm. The second alarm is about 9 seconds after the earthquake occurrence. And we also compared the observed intensity and the predicted intensity. And for our warning cities, the first alarm almost cover all cities or counties in Taiwan, and the second one we issue for the other city. And you can see this figure. The figure here is the time step for every second, and here we just resample the spatial resample by the latitude. So for each latitude cell means we take the maximum observed intensity within this latitude bin, and we just put the observed intensity in the cell. So you can see from here the origin point here is the earthquake occurrence time from here to here, and then you can see in some areas the observed intensity is pretty large, the 6 minus 5 plus. This is the observed intensities, and this figure also can show you the duration of the intensity. So you can not only see the maximum value for final, you also can very easily understand the duration of the intensity. So which is very valuable for you to evaluate the shaking, the damage, the relationship between the shaking and the damage. And then you can see we send out a warning at this point, and the second warning at this point. For some areas, their highest intensity not coming, so still have some leading time for the highest shaking. Okay, this is another earthquake for the Hualien earthquake, another very big one. And this one is the data timing has some problem. So actually here is some data problem. So cause this figure like this. Okay, so I think I need to briefly introduce this because the time is running out of. I will keep my 7 minutes. So we have one problem is about when we have a large earthquake, like the Hualien earthquake with magnitude 7.2, our early warning system maybe underestimated the magnitude in some cases. So in that case, we also underestimated the intensities. So we may miss the alarm. So this is a real case in 2024 with magnitude 7.2 in the earthquake epicenter is around the eastern Taiwan in northeastern Taiwan in Hualien area here. And at that time you can see the warning area is was not included in the northern Taiwan. So it means the Taipei, the metropolitan area, we didn't send any alert for people. But you can see that at that time, our MRT system at that time, the railway has some dislocation. So the shaking is really large for people. People felt very scary, but no warning for people. So we have many pressure at that time. But if we check the observed intensity, you can see this is the observed intensity. It's very clear. You can understand the shaking is really large. So we just thinking maybe our system need to check the real-time observed intensity and use this kind of information to help our system to issue warning. Even our traditional early warning method is failed, but our observed intensity tell us it's true, it's really large, then we just can issue a warning at that time. This is what we learned from this earthquake. Okay, and there's some ongoing projects, like we have some cooperation with the ETH Institute, and we try to use SysCom software to develop another kind of earthquake early warning system. And this system has some features, especially this one. We call it Finder. It can predict the finite fault rupture. So you can see when earthquake occur. After that, we can estimate the direction of the fault line and also the length of the fault. This is very valuable information for us to be more accurate, predict the intensity, because the earthquake is not a point source in this case. The magnitude is very large. It's about 7.2, not a point source situation. So we need to consider the line source. And we also have some cooperate with Professor Masumi Yamada from Kyoto University, and we're trying to incorporate the IPFS method. And right now we have some online testing results. Maybe we can incorporate this kind of method to our system in the future. Okay, we also have some testing projects about using the AI method to predict the intensity. And by using this kind of method, maybe we can use this information to issue earthquake early warning to people. And this is the overview of our system. Here is the computer to receive the data, real-time data from the station. And then we integrate all the data. For duplication, we have 4 computers. Each computer is integrate all the real-time data. Then right now we are running the eBear system. We have 4 computers parallel real-time running the early warning algorithm and determine the location's magnitude. Then we send out to the decision making computer here. EEW ring here, then it will determine the predicting intensity and check the threshold for three channels. One is PWS, the other is TV, and another one is some app for school. Then in the future, actually right now we also have the online operation for the IPFS and some on-site AI modules and for the Syscom system. We also have the online parallel running, but the results are not using for the official early warning system. Right now we're just testing. So I think in the near future, maybe we can add on some new new algorithm to our system, like this methods. Okay. So finally, I want to show this. Our database is free for registration. If you want to use CWA data, you can just register it, and it's free for download. Okay, and I provide some points for discussion. I simply say is one is for proven method. I want to have some discussion with you. How do you use proven method for earthquake early warning system, and how do you use the estimate sensors for magnitude estimation? And the other one is the alert transmission. For our own, right now, if we send a warning, we need about 4 to 5 seconds. People can receive the warning by their cell phone. I want to know some detail about your system, the alert transmitting time. And the other one is phase information obtained. We collected all the real-time data in the central. Then we pick the phase arrival. And I know maybe you have another way. You pick the phase arrival on site in the sensor site. Then you send back the arrival information. Is there any advantage for this kind of method? And finally, just asking if you consider the new technology like DUS for the early warning. So that's all for my talk. Thank you very much. I will share my talk PPT as PDF file for you later. Okay, so thank you.
Okay, thank you very much for the Dr. Chen's presentation. So according to the agenda, so the next talk will by Jma Eew Science, and after the talk we will have the discussion. So maybe the points or question proposed by the Dr. Chen, we can have the more detailed discussion in the discussion sections. So next talk will present by the Okawara-san, right? Okawara-san. So if ready, please.
Can you hear my outside? Hello?
Yes, I can see this.
Okay. So I will start the introduction. So my name is Okawara Nariaki from Psychology and Oceanography Department, Jma. So I will now introduce the operation.
Okawara-san, oh, can I see your PowerPoint file on the full screen? It's just on the. Can you pay the?
Slide show mode.
Wait a moment, please.
Okay.
How
Thank you.
Okay. So I will now introduce the operation of the EEW system in Japan.
So Jma started its e-learning service to the public in October 2007, using seismic observation data from seismometer installed nationwide. The central automatic system calculates estimated seismic intensity and issue forecast. Especially when strong shaking is anticipated, warning are issued and broadcast via television, smartphone, and other means. Details will be explained on the following pages. This is about the earthquake observation network used for the EEW system. In Japan, to issue EEWs, Jma utilized our own network of approximately 700 seismometers and seismic intensity meters, along with approximately 1,000 seismometers installed by MIED. To maintain the observation approximately, continuous data checks are performed. Additionally, regular inspection of observation stations by contractor are conducted every 2 years, and seismic observation facilities are generally replaced approximately every 10 years. Furthermore, to ensure observation can continue for 3 days even if a major earthquake causes a power outage, emergency batteries are connected, and redundant communication lines consisting of terrestrial and satellite lines are implemented. We conduct these checks to reduce the false warning due to noise waveform. We have operational staff who issue earthquake information 24/7. They also visually confirm the waveform. If there are any issues like excessive noise, they manually stop the use of the station, and they resume it if the issue is resolved. Those processes are automated for some stations. The individual stations also perform automatic waveform quality check. Various checks, such as those listed here, are implemented. If any single check is triggered, the waveform is just as noise and excluded from use in the EEW system. Note that the detailed method mentioned in this slide refer to a technique when the rising portion of the absolute acceleration waveform is fitted to a function, such as this function. The delta distance from the station of the earthquake's epicenter is estimated from the coefficient B. If the fitting disturbance is large, the coefficient clearly falls inside the large range typical for a normal seismic waveform, the data is also excluded from use in the EEW system. So when each seismometer detects an earthquake, it performs on-site processing like noise discrimination, maximum amplitude detection, and earthquake parameter estimation. These estimated data and other information are transmitted every second to the central station in a short text format. We call this message ADM. It includes data such as estimated P-wave arrival time, real-time seismic intensity, estimated azimuth, estimated central distance calculated from the coefficient B in the B-delta method, estimated magnitude, and maximum amplitude of acceleration, velocity, and displacement. The text size is very small at 60 bytes, enabling immediate transmission, and the format is designed to be easily usable for subsequent processing. So, the question of which is better, on-site processing or central processing, is depend on various conditions, not just technical aspects. Jma Eew was first designed more than 20 years ago, when broadband lines were not so available. it was not possible to transmit large volume data, and on-site processing was adopted. I think continuous full waveform transmission is ideal at present, but even nowadays, although internet broadband is available with reasonable price, but disconnection may occur after large earthquake. On the other hand, dedicated lines are expensive but reliable after large earthquake, which is better may depend on political decision in addition to technical aspects. So this is about the seismic intensity estimation method for the EEW system. Intensity estimation is performed using a hybrid of the height-centered determination method and the CRAM method, which takes a maximum estimation of both methods. The first is a point source model approach. When each seismometer detects an earthquake, a random message is sent to the real central system. This includes data such as the estimated P-wave arrival time and maximum amplitude. The central system uses them to estimate the hypocenter and magnitude, and then estimates the seismic intensity in each region of the town from the hypocenter and magnitude. The second is a ground method. The AW message also contains real-time seismic intensity data. From the real-time seismic intensity at each station, the seismic intensity within a 30-kilometer radius of that station is estimated. If this estimated seismic intensity is greater than that of estimated in the previous three issued EEW, we update the one. So this is a Jma seismic intensity scale used in Japan. In seismic intensity is classified into 10 levels from 0 to 7, as it is same as Taiwan. Information about earthquake has been released long before the start time of the EEW, so making seismic intensity a very familiar concept among Japanese society. In addition to seismic intensity, information is also released regarding long period ground motion, which describes shaking inside high-rise building. As shown here, the shaking state is classified into 4 levels. So, the EEW consists of warning and forecast, and the criteria for issuing is as follows. Especially when the seismic intensity of 5 lower or greater is estimated anywhere in the country, warnings are issued for areas when intensity of 4 or higher is expected. This threshold is adopted because earthquake with seismic intensity 5 lower or greater can cause personal injury. Furthermore, if long period seismic motion of class 3 or higher is estimated for any area, warnings are also issued for those specific regions. So, while warnings are generally issued only once, if the estimated affected area expands, the warning area may be broadened and the EEW issued. And this is about OBS. We utilize data from the 5 OBSs installed at the Tonankai OBS site here for each EEW system. Additionally, we utilize data from over 200 OBS installed by NYED. Using these OBSs, we can now issue EEWs up to 10 to 30 seconds earlier for earthquake occurring at Great Boundary and in the surrounding area, surrounding sea near the OBS stations. So to use the OBS data, we added 3 additional processes which are unnecessary for land station data. The first one is the collection of altitude angle. Large seismometer can be installed with three fixed directions of up, down, east, west, and north star, but it's difficult for OBSs which are installed without seismic foundation to fix string directions. So, information of attitude angle change must be updated in real time, and correction for attitude angle change must be made clear to regular waveform processing. The second process is the detection of tilting and oscillating, which cause abnormal amplitude. To avoid unexpected large magnitude, when tilting and oscillating are detected, the data is not used for calculating magnitude. The third one is the introduction of a new magnitude calculation formula. This formula uses only an up-down component. Since the vertical displacement, which is integrated from vertical acceleration, is less susceptible to tilting and oscillating, using this formula mitigates the overestimation of magnitude caused by ocean bottom sedimentary layers. In the process of integration or transfer to displacement from acceleration, contamination of gravity by tilt generate abnormal amplitude. This effect is large at horizontal component and small for vertical component. So moreover, to prevent magnitude overestimation, magnitude estimation of ODS is made after multiple ODSs deflect an earthquake. And this is about data and information transmission. Communication technology is extremely important to quickly create information from observed data and quickly transmit the information for public to disaster mitigation. Regarding information announcement, the EEW is transmitted to disaster prevention agency, business, and the public through various communication channels. This information is time critical and each organization is striving to reduce transmission time. When company contact with EEW distribution provider to receive EEWs and use alarm device to notify alert or control operation of railways, machinery, and others, so guideline recommends initiating control action and notice or notification within 1 second of the Jma issuing the forecast. Additionally, companies certified and licensed by Jma processing technical capabilities may provide their own location-specific forecast to their customers. Furthermore, the warning for the EW is widely announced to the public, like this. For example, terrestrial digital television broadcast utilize data broadcasting, which transmit faster than video signal to display a caption earthquake early warning here, this red one, first on TV screen. On smartphone, the area mail function, which is a broadcast mail technique to inform all users within the target area for emergency alert, enable EEW notification within the theoretically achievable shortest time frame, approximately 3 to 4 seconds after the mobile carrier receives the alert. So it's a similar situation in Taiwan. So this is the final slide. I'd like to introduce the reference component, reference document. Sorry that both are only Japanese. The former explains the EW system overview and processing method, including the processing used to distinguish noise waveform and the science intensity estimation method for the EW system, like estimating magnitude and so. The later described techniques for utilizing ODSs. So that's all. Thank you for your attention.
Okay, thank you very much. Okawara sounds nice and the details presentation briefing for your system. So I have the more understanding for you the EW system and the Jma in Japan. So in the following it will be the discussion part. So I think because easy to discuss, so maybe the first the question or comments proposed by the JMA side, do you have some questions or comments for the systems in Taiwan? So please, so any question or comments for us, or more need to understand it, please.
So, first one is data confidence in the ground system. So, so in PLAN method, as a detection of two or more situations is required for public warning, which reduces the false warning by noise. Jma intensity is relatively lowest against noise, in particular spike-like noise, as compared with PGA or PGW. PGA and PGW are instantaneous values result on simulation of duration. For estimation of Jma intensity, duration of 0.3 seconds is taken into account after high passes and low passes data. It's okay?
It's okay?
Yeah, okay.
Okay, thank you very much.
Oshima-san, is there any comment?
Okay, yeah. So regarding the from method used in the Japan, as Ogara-san explained, so even for the from method, we need a multiple station to detect. And one more is a reliability. Is a from method use a Jma intensity. So CWA use a PGA, PGV for seismic intensity, but Jma use a Jma own seismic intensity. So that is estimated from calculation of the acceleration. So which is the process spike lag noise excluded. So that is 0.3 second duration considered, which means PGA PGB is the first largest value. 0.3 second considered means the 30th largest value for 100 sample per S data. You see? This is 30th largest value in the acceleration method. So the process excludes spike lag noise. So Jma intensity is relatively robust against spike lag noise. Do you see?
Okay, thank you.
Okay.
Okay.
Yeah. See.
Okay, thank you. So please, the JMA side, you have some questions or comments for the Taiwan CWA. Okay, no. So I think maybe.
Okay. So
please.
Okay. So I have a now we are about our concern is a deep earthquake in Japan. Deep earthquake means about focal depth 100 kilometers, 200 kilometers, 300 kilometers. So Berlin introduced effective epicenter method, which is epicenter of the detected station, right? Okay. So in a deep earthquake case, in this case, the first detection of station does not necessarily mean a large intensity. So I'm asking, do you have deep earthquake in Taiwan, and do you handle the deep earthquake in a process of the effective epicenter method?
Sure. Because Taiwan is also on the boundary of the two, just like we have the Philippine plate, Eurasia plate. So we also have the subduction earthquake occur around Taiwan. So we have deep earthquake. So now currently the method used just introduced by Dr. Chen, the traditional method used in our EW system. So no matter the zero earthquake or deep earthquake, we also use to get a method to locate, to estimate the earthquake.
So in case of deep earthquake, so abnormally distribution of seismic intensity occurs, which means epicenter region low intensity. Apart from the epicenter region, high intensity. So sometimes occurs the abnormal distribution of seismic intensity in case of the focal depth is quite large. So one of our concern is how to handle the case. So one of the important subjects at present for us. So do you have some improvement to handle the deep earthquake?
I think that the challenge for us the same for the deep earthquake in Taiwan. So maybe, Dai, do you have some solution for the deep earthquake in the EW system? Do you have that?
I think that initially our system still cannot accurately estimate the location or maybe the depth for the very deep earthquake. But if we observe some very large intensity or the PD value, maybe we can use our own effective etcetera method to convert the information into the predicting intensity. And but I want to say is our method is maybe fail for the source parameters. So we were just thinking maybe we need to considering the observed intensity to help us to improve our system.
Do you mean like from the source?
Yes, just
Yeah.
just
I see.
yes. I think it's a good solution for
The
us.
solution.
Yes.
Thank you very much.
Thank you. Thank you. So,
So I have another question.
okay,
So,
please.
in the page 21, you introduced as your ongoing one, line source method. So,
We can find it.
Okay.
can you estimate the line source immediately after earthquake occurred?
Yes, we can evaluate the strike and length in short time. For Hualien earthquake, we just take about 19 seconds. We already can know the strike and the length. And for Hualien earthquake case, we can know the length is about 62 kilometers, and the strike is 20 degrees. And take just 20 seconds. 20 seconds. After origin time. Yeah.
Yeah, it's about 20 seconds after the earthquake occurrence.
Yes.
We can estimate the fault length and the strike of the fault. But we need to have more testing cases to improve.
Line source. Line source. That's great.
So, any question? I think in Taiwan side we have many questions and comments for your system. We have more understanding about your systems. It can teach us a lot. So, do Jma side, do you have any questions or comments? No. So, okay.
Yeah.
Your turn.
Okay. I just have one question. In our situation, after we issue the public warning to people, it takes about 4 to 5 seconds. Their cell phone will get the text message for the CBS cell broadcasting system message. I checked I studied the problem and I realized that the problem comes from the telecom company. Their basement send out the message to the cell phone. It takes time. It takes about 3 to 4 seconds. So I'm wondering what's the situation in Japan? How many seconds do you have for your telecom company to transfer in the early warning message to the normal people cell phone? So
we haven't heard the server company directly, but I think the situation is about similar in Japan. So I hear 3 or 4 seconds, after 3 or 4 seconds, the cell phone being informed earthquake. So I think situation is similar.
Yeah, yeah. Thank you. So I have another one question. If I noticed that in your talk you talk about you have people 24 hours and 7 days to visually watch the seismic waveform, and once the data is not abnormal, you can remove that, and to prevent from your early warning system to use that abnormal data. And but but I also know that you have some your face information comes from the on-site sensor directly. So your early warning system will take the data directly from the on-site sensor, and the on-site sensor also have some kind of algorithm to automatically check the data quality. So how do you manage that you have the automatic quality control? You also have the manual quality control, and your early warning system, how to use those data, how to operate the mechanism. I make my question in short. How do you data quality control for the early warning system?
So later also so the waveform is automatically checked in rough way, and if the wrong waveform detected, the alert is being in the operation system, and the operator will stop the use of the observation point. And we also check automatically so as we mentioned, this can you hear the can you see the slide?
Yes.
Yes. We perform these checks automatically and using waveform, and if one or more if this is maybe there are some checkpoints here is line with maybe 2, 3, 4, 8 points. So if the some error occurs in some checkpoint, the data stops in that observation point. Is it correct?
Yeah. Yes. Yes, I got it. Thank you.
Okay. Thank you very much. Any questions for the? No. I have the question. I just my question is about your seismic network. I think I really admire your seismic network in Japan, particularly you have a very dense ocean bottom seismic network. I have a question. Maybe it's not so related to EW, but you have the stations you call the seismic intensity stations you use in the Jma and some local government, so to provide for the seismic intensity. And the instrument used for the seismic intensity is the strong motion sensors. This is the first question. Another question is the signal will be used in for the EW or some earthquake observation, or only used for the seismic intensity reporting? What is my question, please?
First question, seismic intensity sensor is strong motions.
Sensor is the accelerometer. Three-component accelerometer is the sensor of the seismic intensity meter.
Okay. So the data used in the EW or for the earthquake?
Not only EW, but also, for example, the magnitude estimation. The acceleration is converted to displacement or displacement magnitude estimation. So the intensity. Okay. Jma's strong motion network has an accelerometer. The accelerometer is used both for intensity and also estimation of the magnitude estimation.
Okay.
And the municipalities, local government seismic intensity is just for purpose of the seismic intensity.
Okay, thank you much. I also have a question. So you just introduced, you have the on-site module to calculate for the source. Maybe you can get the arrival time, and you can estimate the magnitude or epicentral distance. So you have the more than 1,000 stations. So every stations in the field stations, you have the module on site to calculate the parameter. Is that correct?
Okay, so some high gain sensors, so for example, high-net and high-gain velocity meter used for the high temperature determinations, and also the strong motion meter is used on a from method once converted to the Jma seismic intensity, and then used on a from method. Okay, so for the purpose of the high gain sensor is used on epicenter estimation in IPF method or something, and also strong motion meter is used on a from method.
So the strong motion data will transmit to the headquarters at maybe in the Tokyo and Osaka, and then to calculate the parameters for the earthquake or on site.
東京と大阪で両方データ送ってますよね。
Yes.
So Tokyo and Osaka is duplicated. The same data is transmitted to both Tokyo and Osaka for backup in case of the one station is something problem. In this case, a backup station immediately backing up the.
Okay, thank you very much. Okay, so. Any questions or comments for the section for the earthquake early morning? Okay, no. So maybe we can move to the next sections about tsunami. So I suggest maybe we have the 5 minutes break, okay? 5 minutes break, and then 5 minutes later we have the for the section for the tsunami. Okay.
Okay.
Okay. Thank you very much. Thank you.
Thank you very much.
他们通常是都不会给。
对啊，不是说他们没有打算让他。
你只有自己来，没有找谁来？小云的还是小云，或者是谁？
详细的不知道反正做的东西。如果会有人，假如会有文件，那就会。对啊，不然我们自己去猜，也不是不让啊，对嘛？如果我们现在如果说我们要引进不让法的话，他要怎么建议我们去让我们跟把不让法弄到的问题？对。然后有没有参考的城市码？ 他都说不定他真的愿意给，也很难讲。对啊，对啊，这是唯一的问题了。其实我觉得这个会议最重要的目的，其实我很期待的是这个，但是我不晓得，对，虽然讲他们可能不一定会理我们，对，对啊。
对他怎么没有写 IPF？
对啊，为什么？
对啊，为什么？我也不知道为什么。
对，讲的好像他们没有这个东西一样。
对啊，只看到他们有。
这样子3个老师会伤心的。
因为3个老师说他们没有用 B data， 可他刚刚又讲 B data。
对啊，还是这个是旧的，就不可能
可是他们的那个2025年3月出的手册有写到 IPF， 有没有看到 B data？
所以我说他们是拿旧的来报，就这批的不是。
那个给你，今天等一下他忘记。好。
我坐这里啊。
你坐这里啊。
我坐这里。
我跟你讲，这场是我听过有史以来理解力最低的，我大概只能理解3到4成，因为我真的没办法去解读成功的解读日式英文，真的，因为我会去猜它这个可能是原本的原型是什么，真的是不懂。对，还好那些术语他有讲出来，不然我很难，我平常聊天很难的，我不聊。对，这场肯定。就是那个不是我们熟悉的那个外国的语言的节奏，对，今年最难的一个战役了，K 没这么难，
是哦，
对，
没关系啊，后北拉。
好气哦，我们很认真的想要学，
只要诚恳就好，诚恳，态度很重要，态度诚恳就可以。不是问题，用笔都可以比得出来，而且都是相同领域的人嘛，
对啦，对啦，
没有那么难沟通。
对，他们有情况，对啦，对。
如果你是餐厅，那就真的很难沟通。
对，日常生活很难，但是这个讨论会可以。等预学5分钟后吗？
他们也有人还没回来。
我有看过，在17分，那个17的。
哦。真的很准时。
很准时，火车什么都很准时。
对，很准时。
我在念不出什么东西哦。
我管你，又不是我报告。不是，你们有这个我根本不知道，是前天才跟我讲说有这个。
大概就时间不要超过就好了，就只要
来啊！
他是怕时间，不是？时间不要超过。
控制好就好，
不要超过。
你就讲。用你的方式讲。
20分钟的样子。
提前结束也可以。
把笑死。
我看他们刚刚也提前结束了。
对，那没关系，
不用讲我。
诚恳就好。
对，诚恳就好。他们那边的收音，就是那个比较大型会议室的收音真的不好。对，那个前辈的另外一个前辈比较资深的一个也做研究的嘛。
说那个
去吧，
好西法是，
他的声音就很清楚，
他就是在麦克
风讲啊，他不会这样吧？
是那个真的。
他们2位有来台湾啊？
对啊，我知道。
哪2位？
这个去吧跟口袋。
对。
刚才那个头发，OK。
那是 ACES 会议。
OK。时间差不多了，那我们就直接开始。Okay, すみません, because time is out, so maybe we start the next section about the tsunami. So according to the agenda, the first talk will be presented by the CWA science, and the presenter will be the Jma Eew, he's the section chief for our centers about his main charge about for the earthquake report and the tsunami warning reporting. So please.
Okay, today I will talk about the tsunami operation at CWA. First, we see the history tsunami record. We can see in Taiwan, north area and the southern area have a historic destroyed tsunami record. And according to our seabed topography, we can see the seismicity. We know that the north part and the southern part have a high risk of tsunami. And according to 做任务 in NCU National Central University, Professor Wu, he has researched that he calculated 18 change type of tsunami source and 4 type tsunami source here in the north part and the south part of Taiwan. And he find that the Okinawa change and the Maria change and the Yap change has a high risk tsunami to Taiwan. And here is the official tsunami message. We can see here is a tsunami message type. Here in the second part is the earthquake and the description tsunami has a assessment. And the third part is most important. And here it has a tsunami forecast for 6 coastal area from northeast and east and north and southeast, southwest and change. Here has tsunami arriving time and tsunami height level. We separated 4 levels from tsunami height. First, level 0 is less than 0.3 meters, and level 1 is 0.3 to 1 meter, and level 2 is 1 to 3 meter, and level 3 is 3 meter and above. And the next part is earthquake information. Next, I will talk about the procedure of tsunami operation. We separate the tsunami from local tsunami and the distant tsunami. The local tsunami is the area is here to 1018 to 1024. Latitude is 20 to 27. In this area, we have a quick earthquake report from CWA, and when we detect a negative over 7 and a deep shallower than 35 kilometers, we use LT feet method to estimate tsunami effect. And we have the data we can organize to official report, and when we make an official report, we use the tsunami report system to offer this message to everyone. When distant tsunami occurs, we receive a tsunami bulletin from PDWC and Jma. When we have the earthquake parameter, we use the rift and the Kamka method to estimate the tsunami time and the level. And also we have made the official report. Here is our report system GUI. We can easy to have our crew can easily to make the report. And when they make report, they can check every detail is that correct. Then I will talk about the tsunami forecast. Here is a lift method is a local tsunami forecast in Taiwan. The initial data is our CWA earthquake, and when detect a submarine earthquake, they have the threat is magnitude larger than 7 and the depth is less than 35. We calculate the vertical seafloor deformation and average the deformation for each unit cell. Then the query pre-compute tsunami database. Then apply the linear combination of a unit tsunami wave and the average deformation. And then we have the data to do the official report. From the Kanka and the rift method, Kanka method is made by Zhuo Renwu in NCU, and the rift method is from Dr. Dailin Wang in PD.C. Here is the procedure. For an earthquake parameter, we use the earthquake parameter and use the free surface deformation, linear acceleration, and have the tsunami forecast. Here is here is when use the Kanka and rift forecasting, we tsunami report system send the earthquake parameter to these two systems, and they forecast the data. Then we receive the forecast data and do some our official report. Here is the decision flow chart for the type of tsunami information. In local tsunamis, we receive CWA earthquake report. When they have they feed the threat, and we issue the tsunami warning. If the distant tsunami message here we receive, and we see the report type. If the report type is tsunami warning, and we estimate the tsunami height larger than 0.3 meters, if the estimated data, we find the tsunami will come to Taiwan in 3 hours, we issue the tsunami warning. If they come in here within 3 to 6 hours, and we issue tsunami advisory, and others will issue a tsunami information. Here is the tsunami simulation products from Russia earthquake. We see the northeast parts and southeast and southwest. These two parts have over 0.3 meters. When tsunami arrived Taiwan, and we find the tsunami wave is closed, we will send a tsunami warning cancellation. Here is our forecast data to here 成功 and东港 and 兰屿 and 小琉球 here. These 4 places here the forecast data, and this is observation data. From this case, we can find the Lanyu here have a 12 centimeter tsunami. Here is a timeline of tsunami warning issue from Russia earthquake. When earthquake occur, this is Taiwan zone area time. So when earthquake occur, after earthquake occur, we send first report is tsunami information, and then we issue the second report, tsunami information, and the third we issue tsunami advisory at 9:12, and then at 11:40 we issue tsunami warnings. And after earthquake 9:45 minutes, we issue tsunami warning cancel at 17:10. Here is a tsunami observation. We have deep sea stations here, Maju and marine cable host observation. We have a pressure gauge in this 9 station, and we have 2 dots, deep ocean assessment and reporting of tsunami from here and here. We also have a software provided from PDWC, is tied to this software. We embed CW deep ocean data into the Thai tool. This case is Tonga by 2022. Is the Russia earthquake, we measure the observation of the pressure, observation of the pressure gauge. Okay, thank you.
Okay, thank you for the Jma Eew the presentation about the tsunami operation at the CWA. And the next briefing will be presented by the Jma side and Okakaki-san, right? Okakaki-san, if you're ready, please.
Can you see the slide? Is it okay?
Yes, okay, please.
Shall we start?
Yes.
Okay. My name is Pira from Jma. I'm going to introduce Jma Tsunami 1 RCP.
画面ごと共有です。
PPT。I'm showing the second part, right? Second computer on Japan. Yeah, Japan has experienced many such activities and tsunami disasters so far. On the right panel, this is on major earthquakes and tsunami disasters. And you can see Japan experienced big tsunami damages by many times in history, roughly 10 to 30 years so far. The event with tsunami casualties are shown in red font in this everything right on bottom. The latest event number 22 happened in January last year at Japan seaside. It was named as the 2024 Noto Peninsula earthquake. And graph shows typical flow of Jma's information after certain size of earthquake occurs near Japan. If seismic very fast we issue earthquake value warning you discussed just before. And then if seismic intensity of 3 or greater is observed, Jma issues seismic intensity information within 1.5 minutes. It triggers Japan's government to make emergency responses. Then, if tsunami threat is found anywhere in Japan, Jma issues tsunami warning or advisory within 3 minutes after the earthquake origin time. Even if no tsunami threat is found, Jma announces stop this step. I mean 3 minutes. This graph shows the long-term trend in elapsed time for tsunami warning, and that is how long does it take from the earthquake detection to issuance of the first tsunami-related Jma. In 1950s, it was about 17 minutes, and then in 1983, a tsunami generated in the Sea of Japan reached its west coast in about 7 minutes. To address this issue, Jma introduced a computer system for data processing, and the elapsed time gets shortened to about 7 minutes. In 1993, earthquake off southwest Hokkaido, it reached some force before people heard Jma's warning. So Jma further updated its seismic network and introduced a quantitative tsunami prediction system. The current method, Jma is now applying numerical simulation database techniques. Sorry? Can I go ahead? And you can issue tsunami warning within 3 minutes now. Let me introduce the immediate response on issuance of tsunami information. When detecting an earthquake, we first estimate the center's magnitude in 1 or 2 minutes,
Next, using the earthquake parameters database shown number 1, we estimate the expected tsunami height and issue a warning if necessary. Soon after that, Jma announced its expected tsunami height and estimated arrival time. In parallel, using newly reliable seismic data, we perform double phase and CMT analysis to determine more reliable center and moment magnitude and fault mechanism. If this analysis indicates the initial issuance might be underestimated or not so correct, we update the warning based on the new situation. Subsequently, we continuously notify tsunami height from offshore water pressure data, GNSS buoys, and coastal tide gauges to share the latest situation with the organization and the general public. I've talked about the tsunami database shown in the previous slide. Since the numerical simulation takes time, we established the database in advance, which contains relations between earthquakes and possible tsunamis which reach Japan's coast. We prepared many kinds of earthquakes defining the center, location, depth, and magnitude. Then we simulate the tsunami propagation caused by such earthquakes and save the simulation result in the database. The number of calculated scenarios is about 100,000. And when an earthquake occurs using the analyzed hypercenter magnitude, we search the database and pick the similar scenario among them. By using the search result, we can estimate tsunami height in all coast Japan in a few minutes. This is a detailed explanation of the database design. Scenario types are composed of combinations of location, depth, and magnitude. Location of the assumed faults are set as shown in the right figure, set at the interval of 0.5 degree near the coast and 1.0 degree at the area on the farm. Strike angles of the fault have been set along the trench. If no trench identified on the grid, it was set along the coastline. And also we need to know the fault mechanism to get the sharp tsunami source, but it generally takes more time, more than 10 minutes to get enough data to estimate the mechanism, while we have to issue early warning as early as possible. Jma prioritizes safety and avoiding underestimation. So the mechanism in the database is fixed to reverse fault with a dip angle of 45 degrees, but tsunami height tends to be high. Next slide will the information framework. Jma announced its tsunami threat in 3 categories to estimated according to 3 categories according to the estimated wave height. Major tsunami warnings are issued when the wave height exceeds 3 meters and shown in purple color. Tsunami warnings correspond to over 1 meter and tsunami advisories with over 0.3 meters. This category is shown in each color, and so the warning is in red and advisory is yellow. In the case of big earthquake, like magnitude more than around 8, we cannot determine magnitude in a few minutes. So even though in such case we can know high tsunami risk and we need to alert people immediately.
So we first issue warning with expression like huge or high without specifying numerical figures. As for the regional resolution of the warning, they may divide the transport into 66 blocks and issue warnings for each block. The blocks are shown in the right hand side this page. And there are additional information to complement the warnings to help people understand the latest situation. Those information include high tide time, observed tsunami height, tide gauges, or offshore sensors. This is an example of tsunami warning issued in Noto Peninsula earthquake last year. It occurred at 1610 Japan time, and that time, and the first tsunami warning was issued in 2 minutes and 16 and 12. Then a minute later, the tsunami warning in Peninsula was upgraded to a major tsunami warning using the updated earthquake magnitude. While continuing to monitor the sea level data, they may cancel the tsunami warning the next day, 2nd January. Bhutan's distant tsunamis, it is less necessary to issue warnings very quickly. So after detecting the earthquake, we evaluate the potential tsunami impact on Japan using data from seismometers and IPS worldwide, and then issue the necessary warning and information. This is a timeline in response to distant earthquakes and tsunamis. And Jma determines the centered magnitude about 10 minutes later from origin time and evaluates the tsunami risk to Japan Islands. In about 20 to 30 minutes, we issue distant earthquake information. It mentions the earthquake parameters and whether tsunami damage is expected to Japan or not. If a tsunami threat is expected, we issue a warning about 2 hours prior to the estimated time of tsunami arrival. Even before the issuance of the warning, we notify the public that the warning will be issued so that people can take necessary actions such as preparing for potential evacuations. This is an ultimate response to the earthquake of the Kamchatka Peninsula this July. Here the time is shown in universal terms. So the origin time was 23:24, early 9th July. It corresponds to 8:25 now. So, and the first estimated magnitude was 8.0. We issued the first tsunami advisory of 23:37. Then using more seismic data, the magnitude was changed to 8.7. And based on this new magnitude, we upgraded the advisory to tsunami warning at 0040. And soon after that, we held a press conference to explain the tsunami warning and let the people know the current situation. At 11:45, the evening of Japan Standard Time, warning was cancelled and downgraded to advisories. The advisories were cancelled on the following evening However, a sea level change continued to be observed. It was recommended that people engaging in activities by the sea to pay attention to the presence of low waves and currents. This graph shows waveforms of some situations during the event. The red dotted line here shows zero between midnight of 30th July in Japan time and approximately 16 hours after the expectation time. The red triangles show time marking the maximum wave height at each station. So you can see the high sea levels lasted for more than 1 day in many stations. And here are challenges we found on this event. First, this was a large-scale earthquake in distant area, and it was difficult to quickly determine the accurate magnitude. After issuing the first advisory, it was upgraded to warning. Since some people might have only seen the initial advisory, we used press conference to hold control as many people as possible. We also held subsequent press conference to explain the situation. Second, sea level fluctuations continued for many hours, more than a day, and it was difficult for some people to stay in highland area for a long time. So we emphasized the need to continue evacuations while also taking care of their health condition. To effectively utilize tsunami warning for disaster mitigation, people's actions are critically important. In this sense, Jma has been challenging people to take actions in order to save lives from tsunamis. Research shows an example of Jma's public materials. It aims to notify people's action to be taken when they see or hear a tsunami warning or feel a strong shake in the coast. This is some example of Jma's effort in raising public awareness to earthquake and tsunami. Thank you very much. That's all.
Okay, thank you very much for the very nice presentation by the Okakaki-san. So currently, the next will be the discussion session. So first, maybe the Jma slide. Do you have any questions or comments for the presentation of the CWA?
Thank you. So let me think. Question in a minute.
Please.
I have some question and I ask questions.
Okay, please.
Thank you for your presentation about CWA's operations. You mentioned you operate some system like on recording system, deep, and something like that. But do you implement those systems by yourself, or you're working with some private companies or some consultants? That's my first question.
Okay. So maybe I answer the questions because our main cooperation with the professor in the university, so they help us to develop the methodology, how to simulate the tsunami height or the arrival time, and then they have the transfer the technician to the CWA. Then we implement our systems by ourselves. So we have some colleagues in our centers. They have learned how to implement the system and learn how to deal with the technology to simulate the tsunami height. So the method is from maybe from the PwC or from the Scholars University, and then the system is implemented by ourselves. Or is our answer. Thank you. 你要补充？小鱼刚才没错了。Okay. Yes. So any questions?
So you are working with universities in Taiwan, right?
Yes.
And my second question is, how have you ever been issued the tsunami warning for over 3 meters or such a big tsunami or estimated so far?
Pardon. Can you say more once?
And have you ever issued tsunami warning
You
over
have
3
been for the tsunami higher than 3 meters? No, not yet. No, not yet. In Taiwan, in my case, I have entered the central with the administration for 30 years. Me. But the tsunami warning we issued maybe 2 times or 3 times. And the first time we issued the tsunami warning is in the Tohoku earthquake 2011 for Japan. So I thought maybe in the environment, the technology environment around the Taiwan area. So it's not easy to have the accurate, very high tsunami in Taiwan coastline, because the strike fault or the subduction boundary is not toward the Taiwan Islands. So it's not easy to have the accumulate the height tsunami in Taiwan area. So currently we did not issue the warning with the tsunami height than 3 meters. No, not yet. And actually, we only 2 times or 3 times for the last 30 years we issue the tsunami warning. So compare with the Japan, the tsunami with challenge or threatening is not so high than as Japan. So the tsunami is not so high threatening for Taiwan. It's not the case currently in Taiwan.
Thank you. So, what kind of damages or impact are you expecting with tsunami in your country?
The latest one, historic tsunami damage in Taiwan areas back to the 150 years ago. The really caused the tsunami damage in Taiwan coastline. The real case, the truth is in the 1867 years, about 150 years ago, in the northern part, in Keelung, northern part of Taiwan. So it's now the historic records for the tsunami damage in Taiwan. Yes.
Mm-hmm. Thank you. So I guess you may have some challenges to let people know the tsunami risk in Taiwan. And how do you deal with that challenges?
I just mentioned that because the tsunami certainly is not so high in Taiwan, but because Taiwan is surrounded by the oceans, and we also in the active zone, seismic active zone. So the tsunami, we also care about the tsunami. So we just have some developed some of our systems. If we have some regulations about the tsunami, just mentioned by the the Jma Eew that mentioned about this. So how to say that we deal with the tsunami just like we have some reference learning from the Japan case or from PwC to implement our system and our operations about the tsunami in Taiwan. So just not so really real case, but we still from some learning from some other countries. So we develop our system, and also with the collaboration with some execute emergency agency. So where we saw the cooperation, then we will issue the tsunami warning, they can miss the message and arrange how to evacuate the people in Taiwan. So we have some national drill in September every year. So if we issue a tsunami warning, the people how to evacuate to the safe place, we have the drill about this. But the real one is not so often in Taiwan. This case is real. Okay.
Thank you very much. So I have another question. So you mentioned you estimate up and down of the ground and estimate with the linear combination of calculation. So you mean that you immediately calculate the ground up and down, and then using a linear combination, you predict what height of tsunami is predicted, estimated, right? In Japan, we estimate latitude, longitude, magnitude, depth, and only from that we pull from database and we say tsunami warning or alert. So how about Taiwan?
Yes, in the local case, if the earthquake or is not so far away Taiwan, we use the database. We use based according to the source parameter, the earthquake, and the location, the magnitude, or some depth, something like that. So we extract the database, just like Japan, the same case. Database, and then we based on the database to issue the tsunami warning to the coast area. But for the distant tsunami, we think we still have time. So we use the real-time simulations for the impact for the tsunami, including the arrival time or tsunami amplitude, then to determine whether to issue the tsunami warning or not. Now is the current methodology we use in Taiwan. Yes.
The simulation is similar. In Jma Eew, we perform real-time simulation on distant earthquake. And now we challenge we have a challenge to do it in near Japan in two or three or years later. We are now challenged.
And so it's also the same challenge for us. I think it's the same situation in Taiwan.
Near Japan earthquake, doing simulation, real-time simulation. So, which case you use
linear combination of unit tsunami. You mentioned in your slide. Can you see your slide again?
Oh,
I forgot the page number, but
you means the method that we use to simulate for the forecasting the tsunami simulations? Oh, units. We also use the CONCOM method. CONCOM method. Developed by the Cornell University, right? CONCOM. Yeah, by the Professor Liu, the CONCOM method. So we use the method to generate our database.
excuse me, can I, could you, is it possible to show, can you show your slide, describing the database again?
Okay, sure. 那个
上面这样。
这个
Yeah, this one.
yes.
Local tsunami focus one. Earth quality information. Average information is there. Waves.
乔伊，你要救我，这个问题的时候。
没有，有一张写到看看。
没关系，就这个就好。这个也是用卡卡算的，这也是用卡卡算，就因为这就模拟出来。
提到看看的名字。这边没有。
In this slide, we how to create a database, right?
Yes. In our
Okay.
this database and the method we also use the COMCAT to simulate the unit, every unit, to generate our database for the tsunami.
Okay, thank you.
Okay, thank you. So, any questions or comment for us for CWA? Okay, so now our turn. So please, do you have any questions for Jma, please? No? Okay, please.
Okay. I noticed that you mentioned that you start to use earthquake early warning system information into your tsunami warning system. So do you apply the magnitude which generated from the early warning system and directly use that one for your tsunami simulation? Because you mentioned that when the earthquake is pretty close to the Japan coastline, maybe you don't have enough time, and your traditional method maybe underestimate the magnitude. But your early warning system maybe have some different method to estimate the magnitude more accurately. So how do you use the early warning information for tsunami simulation? That's my question.
Thank you very much. Yeah, basically the magnitude and location to issue early warning system is delivered to tsunami database. So the magnitude and center will be used to database search in the tsunami warning system. So that might be earlier by about 30 seconds or so than the normal magnitude and information from the ordinary, normal tsunami early warning system.
So it's not so bad to estimate magnitude or density near Japan or inland Japan. So we use this. With the earthquake, some far from Japan, it is slightly difficult estimate likely to estimate magnitude of this. So if we it's I feel far from Japan. We don't use this. We normally estimate magnitude and issues number.
Yeah. Because the source parameters from the early warning system maybe have higher uncertainties. So how do you evaluate the quality, or how do you have the confidence to use the source parameter directly from the early warning system? That's just what we are facing the problem. Right now we don't directly use the source parameters from the early warning system for tsunami simulation. So I'm just wondering, how do you evaluate the quality of the source parameter from the EW system?
Basically, the earthquake occurs very close to Japan. But in that case, the magnitude and location of early earthquake warning is not good.
So we use it. We try to use it near of the land. Automatically use.
Okay.
So in Japan, warning is very important. Evacuating people is very important in Japan. Japanese society is very important. People know everything about this. So even if we estimate higher magnitude here, it's just.
Okay, thank you.
And I have a question about your tsunami operations. Just as you mentioned, your operation, then you issue the tsunami warning, then you will begin to calculate more reliable magnitudes, like the moment magnitude. Then we will do some updates about your warning or adversary, tsunami warning or adversary, based on you have the real reliable magnitude. And then you also use the real time observation data from the tsunami meters. Of course, just because you have a very dense ocean bottom seismic network and pressure gauge like the SNAT, ANAT, or DUNAT, you also have GNSS stations, GNSS buoy. So you have the real-time observation for the tsunami. So when you have the real-time observation for the tsunami amplitude, tsunami record waveform, how do you to update your report, your warning or adversary? Is my question.
Thank you very much. I understand your question. So if the real observation of offshore sensors or GNSS sea level sensors exceeds the
Operation.
yes.
So we update if the operation is lower than observation, we update soon update the warning.
So what's the correction? Correction. So for the your sea floor, sea bed, the pressure gauge data, between the correction and the offshore the tsunami height. What's the correction? Correlations between.所以你只要看到那个妈祖的那些神社，看到
可以做，但是前提是
讯号要好，对不对？
对，而且它刚好是在那个能量这个方向上修正才有意义。
哦，反正有这个功能就可以做。他们是有在做，他们把他们实际收集的对。
Hello.
Yes.
Yes. When we observe tsunami height in the offshore sensors,
Yes.
Depending on the location and the sea level of the station, we estimate the tsunami wave height at the coast. And if the estimated value exceeded the previously issued warning, we will revise the warning. So we know the relation between the offshore values and the coastal wave height in advance.
Okay, thank you very much. So, okay. Okay, so any questions or here?
Here I have a question. When you publish a tsunami warning, how can how and when to determine to cancel the to issue the cancel report?
Are you asking how we decide to cancel the warning?
Yes.
Yes.
Yes. Yes.
Basically, the observation part. I mean, we monitor the sea level data at aggregate stations, and generally getting lower and lower in the time goes by. And we also do simulations, and we will compare the result of simulation and observation. So, integrating in those information, we decide we can cancel or we should continue to find that. And we the tide lower than 20 centimeter or so, and we cancel warning.
Thank you.
Okay, thank you.
How about you? How do you decide to cancel warning?
We find the tidal gauge data and see the change and do the decision.
Sorry, can you say it again?
Okay, we have real time tidal gauge data, and we see the sea level, and we find when tsunami occurred time, and we after the tsunami occurred time, we see the sea level change. If we think the tsunami is past, we alert the cancel report.
Thank you.
I think it's just the same methodology, I think, but because I just mentioned that because the case, tsunami case, to issue a tsunami warning in Taiwan is not so often, so we maybe have more experience from Japan to tell us how we can cancel the tsunami warning. Yes, it's something.
In Kamchatka case, tsunami is very long.
Yes.
Period. Only very long period. So I said we wait until the tsunami gets lower from about 20 centimeters. But the Kamchatka case, we canceled tsunami even the tsunami is greater than 20 about 50 centimeters or so, but continuing tsunami warning, efficient social society, so we decided to cancel tsunami in evening, because if we cancel even if we cancel tsunami evening, people will not beach or seashore. So we decided to cancel tsunami. I don't advise.
Okay, thank you very much. So, for more questions or comments for both sides about the tsunami section. Okay, so now according to the agenda, we made the next one is the closing. So, the Jma side, do you have some remarks or words for us for today's meetings?
This is Yasin from International Affairs. Today, thank you very much, and it's a very efficient discussion and very useful for us. And also, if you have any question or any other question or more, we need more discussion, please send me the email for me. And after that, continue the discussion about this each topic. Anyway, if you have any question, please give me the email. And also, Aji-san already mentioned about the shared document, presentation file. I will send you the document later. And also the picture, the screenshot at the first time. Thank you very much.
Thank you very much.
Well, thank you. I'm very glad to hear that this is the meeting, although it's the first one, but it's not the last one. So we may have more communication in the future. Actually, I really have some questions about your operations, such as your LPGM, long period ground motions, or your Nankai Chua extract information. So I also have the interest about your operation in the JMA. So you may have made some insight for us. So if possible, we also have more meetings like this online meeting, like this one. So in the futures, and also we sincere to invite you if you have the chance or have the interest to visit us, please tell us. We can arrange your visit if possible in Taiwan at the CWA. So thank you very much again for today's meeting and arrange for the very nice communication, and we hope we can have the cooperation if possible in the futures. So should we stop the meeting here? And any questions or remarks or words for us? No? No? So we may stop the meeting here. どうもありがとうございます。Thank you very much. Okay, 谢谢。So we start the meeting here. See you soon. See you soon. See you soon. Bye bye.
Bye bye. Thank you.
Thank you very much.
我去打扫 Thank you. Bye bye. Thank you. Bye bye. 口天屋さん Bye bye. 最后一个离开，看你离开吗？
他们都比慢了，他们不离开都比慢。好了，那就这样。为什么有今天这个会议？为什么这个？
那以前都是气象跟他们开线上会，气象
类似这样子啊。
气象跟JMA开线上会已经好像2、3年了。然后去年。他是透过台日经贸协会去跟 JMA 沟通的，我不是直接跟他沟通。然后去年就那个，去年那个沈家平，我想说换地震，让地震来 meeting 一下，所以就今年改成地震这样。一开始他们也不太愿意讲地震，他们还想要继续讲气象。可是预报中心的科长也跟他说不行，一定要讲地震，他要拒绝那个 JMA， 跟他说一定要讲地震。
他们这些人都是地震部门的，地震海啸部门的，不是气象的人这样子。
对，是今年是，但是他应该会1年地震1年气象，那时候有这样讲。
他不是说你们有兴趣可以 mail 给他，可以来看。你们有兴趣的。
所以明年应该 online meeting 是气象。
OK， 好了，谢谢各位，辛苦了，谢谢。